Hi, in this video I'm going to be showing you how to prove that the midpoint of a line in 3 dimensions has the coordinates x1 plus x2 divided by 2, y1 plus y2 divided by 2, and z1 plus z2 divided by 2. Now, to get this proof you need some ingredients. That is, a circle with a radius and a few right-angled triangles. What is also required is 2 angles and also some specified points. You also need to know SOHCAHTOA. So let me explain this diagram carefully. We have 2 right-angled triangles. One is in the Z1 plane, okay, and the other pokes out of the Z1 plane. Okay, and using these 2 right-angled triangles, we're going to be able to specify the midpoint of a line in 3 dimensions. Now, the right-angled triangle in the Z1 plane is going to have the angle theta, the hypotenuse r, the adjacent side with the length x2 minus x1, or r cos theta, and the opposite side with the length y2 minus y1, or r sine theta. Also, the right-angled triangle poking out of the Z1 plane is going to have the angle phi, the hypotenuse d, the adjacent r, and the opposite side as z2 minus z1, or d sine phi. So let's just recap a couple of things here. We are going to be using 2 right-angled triangles, 2 perspectives, to find the midpoint of a line in 3 dimensions. What we've discovered is that r cos theta is x2 minus x1, r sine theta is y2 minus y1, and d sine phi is z2 minus z1. Using this information here, we are going to be able to find that midpoint very, very easily. Now, to find the midpoint of this line in 3 dimensions, we first need to find the midpoint of this line over here in 2 dimensions. Now, the x-coordinate of the midpoint of this line in 2 dimensions is going to be x1 plus half times r cos theta, because we're getting the half of this adjacent side over here. The y-coordinate of this midpoint over here is going to be y1 plus half r sine theta. That is because we're getting half of this opposite side over here. And remember, we start from x1, y1, because these angles are over here. Now, for this midpoint, the coordinate x is x1 plus half times r cos theta. Because r cos theta is x2 minus x1, for this coordinate we get x1 plus x2 divided by 2. For the y-coordinate of this midpoint, we have y1 plus half times r sine theta. Now, because r sine theta is y2 minus y1, for this y-coordinate, we get y1 plus y2 divided by 2. If you want to check these equations, feel free to go back and pause this video. Now, to get the midpoint of the line in 3D, all we have to do is connect the line that is perpendicular to the midpoint of this line over here to the line that is perpendicular to the point which is the center of the difference of z. So what we're essentially doing is connecting this line to this line over here, and where they meet we have the midpoint of the line in 3 dimensions. Thankfully, we have already found the x and y coordinates of this midpoint. Now remember, this right-angled triangle is poking out of the Z1 plane. So this distance over here is going to be Z2 minus Z1, or it's going to be d sine phi. Now let's get that Z coordinate. What it's going to be is Z1, because we start from the Z1 plane, plus half d sine phi. Now because d sine phi, as I said before, is Z2 minus Z1, what we get is this equation over here, and it simplifies to Z1 plus Z2 over 2. Since we already have the x and y coordinates of the midpoint of this line in 3D, we can say that the coordinates of the midpoint of this line in 3D are x1 plus x2 over 2, y1 plus y2 over 2, and z1 plus z2 over 2. And we've shown, using geometry, that this is indeed the case. If you want to see more geometry and mathematics videos like this one, then make sure you are subscribed to my channel. For extra mathematics proofs, as always, visit mathematics.proofs on Instagram. If you have any comments or questions, leave them in the comment section. Thanks for watching this video, and I'll see you next time.